Welcome to Wisdom Docs. Settle in. Let the lights go low, let the pillow take the weight of your head, and let your breathing slow down to match the pace of my voice, because there is nowhere to be tonight and nothing to solve. We are going to a lake. A quiet one. A round sheet of dark water lying in a green hollow in the west of Germany. So still on a windless evening that the trees along its far shore hang upside down in it, doubled and perfect, and the whole surface looks less like water than like a pane of old glass laid flat across the land. There is an abbey on one shore, its bells old and unhurried. There are reed beds, there are footpaths and benches, and the small sounds of an ordinary European evening. If you stood there tonight, you would think you had found one of the calmest places on the continent. And you would be right. But you would also be standing on the lid of something, and tonight, very slowly, and without any hurry at all, we are going to lift that lid. Come down to the southeastern edge of the water first. This is the corner to notice. The shallows here are gentle, the bottom shelving away by inches, and if you crouched at the margin on a still morning and simply watched the surface, you would begin to see it. Bubbles, not many at first. A thread of them, rising in a slow silver rope from somewhere down in the mud, breaking the mirror in tiny rings that widen and fade. Then another thread, a little way off. Then more, scattered across the shallows, faint columns of gas climbing up through the clear water and quietly leaving it. In some places the sand on the bottom trembles with them, as if the lakebed itself were simmering on the lowest possible heat. It looks like the water is faintly boiling, though it is cold. It looks, if you let yourself think it, as though the lake were breathing. Slow, patient breaths, released from the ground beneath. Those bubbles are not air, they are carbon dioxide, the same heavy gas we breathe out, the same gas that puts the fizz in sparkling water, and it is coming up out of the earth here from a very great depth. Geologists have a small, old word for a place where gas seeps up through the ground like this. They call it a moffett. A moffett is simply a cold vent, a spot where a volcano exhales its gas, without any fire, without any heat you could feel, without any drama at all, just the quiet, continuous escape of deep breath through soil and water. And that is the first thing to understand about this lake, the thing that reorders everything else you will hear tonight. Those ribbons of gas rising through the southeastern shallows are not a curiosity, they are a message. They are the lake telling you, plainly and without alarm, that the volcano underneath it is not dead, it is only sleeping. And even in its sleep, it exhales. The lake has a name, it is called the Laacher See. Laach, an old word for the place, See, the German word for lake. Lake Laach. Say it slowly and it settles into something soft, almost drowsy. And this lake, this soft-named sheet of water with the reeds and the abbey bells, sits inside the collapsed throat of one of the largest volcanic eruptions Europe has seen in the last 100,000 years. The still surface you are picturing is not resting in an ordinary valley scooped by a river or left behind by a glacier. It is resting inside a caldera. A caldera is what remains when a volcano empties itself so violently and so completely that the ground above the drained chamber has nothing left to stand on, and the whole roof simply sinks, collapsing inward to leave a great rounded basin where a mountain of magma used to be. Picture an enormous underground room that empties in a single terrible night, and then the floor of the world above it dropping into the hole. The bowl that is left fills with water over the centuries, and what you get in the end is a lake. A beautiful, circular, deceptively peaceful lake sitting in the scar. The scar here is about 2 kilometres across. That is the width of the caldera, the round rim of high ground that cradles the water, a little under an hour's slow walk from one side to the other if you followed the shore. The lake itself covers roughly 3½ square kilometres, a modest size as lakes go, small enough to see clear across on a bright day. It reaches down about 53 metres at its deepest, which is deeper than it looks, deep enough that the water at the bottom stays cold and dark and undisturbed for most of the year. And the whole thing sits about 275 metres above sea level, cradled in gentle hills, in a landscape of woodland and farmland and small stone villages that gives no hint to the passing eye of what it is. You can place it on the map without any trouble. It lies about 24 kilometres to the northwest of Koblenz, the city where the river Moselle meets the great river Rhine, in the German state of Rhineland-Palatinate in the country's western reaches, not far from the borders with Belgium and Luxembourg. This is soft country. Rolling, green in summer, misted in autumn, the kind of landscape that appears on the covers of gentle travel guides. And it belongs to a volcanic region called the East Eifel Volcanic Field, a name we will return to and unfold and sit inside for a good while before the night is over. For now, only hold this, a calm lake, 2 kilometres of caldera rim around it, 53 metres deep, 275 metres up, 24 kilometres northwest of Koblenz, breathing gas from its southeastern shallows. Hold that picture the way you would hold a warm cup in both hands. And now let me put to you the question that will quietly run underneath everything else tonight, the question that makes this lake stranger than almost any other place I could take you. If this is true, if this quiet water sits in the throat of one of the biggest eruptions in European history, if it is still exhaling volcanic gas today, if it is by any honest measure a giant, then why have you almost certainly never heard of it? Why is there no famous name here, no household word, nothing that leaps to mind the way certain other volcanoes do the instant they are mentioned? A mountain of comparable power anywhere else in the story of the earth would be printed in every schoolbook. This one is a footnote. A local beauty spot. A place people paddle in on summer afternoons without the faintest idea what they are floating on. That gap, the enormous distance between how powerful this place is and how little it is known, is the real mystery we are going to wander into. Not will it erupt. Something quieter and far more interesting than that. How does a giant hide? How does something this large stay this invisible for this long? We will get there. We have all night, and I want to take the long way, because the long way is the whole point. So before we go down into the rock, let me ask you something small and warm. The kind of thing I like to ask when we first push off from the dock. Tell me, in the comments, where in the world you are listening from tonight. What time is it where you are, and what does the dark look like out your window? I read them, every one, and there is something I find quietly lovely about a scattering of little lights all over the globe, all of them lying in the dark, all of them drifting toward sleep over the same slow story. And if you are new here, if you have only just wandered onto this dock, you are very welcome. You might tap the button to stay, so the next slow story finds you when you need it. That is all. No more asking after this. From here on it is just the two of us, and the lake, and the long descent. Here is my promise for the hours ahead, and it is a gentle one. I am not going to frighten you. There will be no sudden loud moment, no jolt, no stinger in the dark meant to snap you back awake. That is not what this is. What I am going to do instead is lead you downward, one slow layer at a time, from the calm surface of the water toward the fire that made it. And I want you to notice that as we go deeper, the evidence gets quieter to the senses, but louder in meaning. First the bubbles, which you can see. Then, far below, earthquakes too deep and too faint for any human body to feel. Then, deeper still, the engine itself, a column of hot rock rising from a place so far down it is hard to hold in the mind. You are allowed to fall asleep at any point along that descent. In fact, I hope you do. The story does not require you to reach the bottom. It only asks you to relax your grip and let yourself sink, the way a stone sinks through still water, slowly, turning a little, in no particular hurry to arrive. So let us widen out from the lake, gently, and take in the country it belongs to, because Laacher See is not a lone oddity. It is one member of a family, and the family has a name that is worth saying aloud in a hushed voice. The Eifel. The Eifel is an upland region of low mountains and plateaus in western Germany, spilling toward the borderlands, and across much of it the ground is not ordinary ground at all. It is volcanic. Scattered through these gentle hills are the marks of fire. Old cones softened by grass, round hollows brimming with water, springs that fizz straight out of the rock, dark stone that was once molten and is now built into churches and farmhouse walls. So thoroughly is this landscape shaped by old volcanism that a part of it now carries the name openly, without embarrassment. The Volcaneifel, the volcanic Eifel. A whole district of Germany named for the fire beneath it, as calmly as another place might be named for its rivers or its woods. And the fire has not all been of one kind, which is why geologists divide this country into two neighbouring provinces, two fields of volcanism sitting side by side. To the west lies the West Eifel Volcanic Field. To the east, our field, the East Eifel Volcanic Field, the one that holds Laacher See in its scar. The two fields have different tempers, different signatures written into the land, and the difference is best read in the shape of their lakes. Because the Eifel, both halves of it, is a country of strange round lakes, and to understand this landscape you must understand how those round lakes are made, and the way they are made is one of the loveliest, most unexpected small facts in all of geology. Out in the West Eifel especially, the hills are dotted with them, near perfect circles of water, deep and cold and quiet, sitting in the fields like coins dropped from a great height. From the air they look almost artificial, too round to be natural, a scatter of dark eyes gazing up at the sky. They are not craters in the ordinary sense, not the open mouths of cones that built themselves up in layers. They are the opposite kind of volcano. They are holes blasted downward into the flat ground by a single violent meeting of two things that should never meet, rising magma and groundwater. Picture it slowly. Deep down, a finger of molten rock pushes upward through the crust, and somewhere on its way it strikes water soaked into the rock and soil above. The heat is so sudden and so extreme that the water does not simply boil. It flashes to steam in an instant, and steam takes up vastly more room than water, hundreds of times more, and all of that expansion has nowhere to go but out and up. The result is an explosion, driven not by lava but by steam, a single downward blast that hollows out a round pit in the surface and throws a low rim of shattered rock around it. No mountain builds. Instead, the land is punched inward, and then, quietly, over the years that follow, rain and springs fill the pit, and what was a wound becomes a mirror. A round, deep, gentle lake. That landform, the water-filled crater made by a steam explosion, has a name used by geologists all over the world, in every language, on every continent where such things are studied. The name is Maar. And here is the small warm marvel I promised you. That word was not coined in some distant university and shipped out to the Eifel to label its lakes. It went the other way. Maar is a local word. It comes from the dialect of this very region, an old Eifel term the country people here used for these round pools of water long before any scientist arrived to classify them. When geologists first came to study these strange circular lakes and needed a word for the thing itself, they did not invent one. They simply borrowed what the people of the Eifel already called it. And so a piece of the everyday speech of these hills travelled outward across the whole of science, and today, when a volcanologist in Japan or in the Andes or in the American West describes a steam-blasted crater lake, they reach, perhaps without knowing it, for a word first spoken in the fields of Western Germany. This landscape did not just make the landform, it named it for the world. The Eifel is, as the geologists say, the type locality, the home ground, the original example, the place the very idea was taken from. Let that settle for a moment, because it tells you something about where we are. This is not an obscure corner that volcanic science overlooked. This is one of the places volcanic science came from. The people here have lived among these round waters for so many centuries that they gave them a name in their own tongue, and that name outgrew the valley and went out to describe the whole planet's version of the same thing. And yet, here is the strangeness again, circling back. Even this landscape, this named and studied and word-giving landscape, keeps its largest secret quietly. Because the Maars of the West Eifel, lovely and deep and round as they are the small work, the gentle work. A maar is what you get when a modest pulse of magma meets groundwater and blows a single pit. It is a firecracker compared to what happened in the eastern field at our lake in the caldera 2 kilometres wide. Because Laacher See is not a maar. It is easy to assume it is, sitting there so round and so calm among all its maar cousins, and many people who visit surely think of it as just another of the Eifel's pretty crater lakes, a little bigger than the rest. It is not. A maar is carved by steam in an afternoon of violence and then falls quiet, often forever, having spent its one small charge. Laacher See is the throat of a true magmatic eruption, an event of an entirely different order, one that did not merely puncture the ground, but drained a great chamber of molten rock from kilometres below and dropped the roof of the world into the empty space. The round shape misleads you. The calm misleads you. Everything about the surface is designed, by nothing but time and water and grass, to make you underestimate it. And that, again, is the pattern we keep meeting and will keep meeting all the way down. The deeper truth here is always quieter on the surface than it is in fact. The bubbles look like nothing. The lake looks like a beauty spot. The maar looks like Laacher See's equal. And every one of those appearances is a gentle lie the landscape tells. So sit with the difference between the two fields for a little while, because it is a restful thing to hold. To the west, the Maars, the small round eyes of steam, scattered and shallow-tempered, each the mark of a single brief meeting of fire and water. To the east, the deeper machinery, the province that could build a chamber of gas, charged magma, and empty it in a single catastrophe and leave a caldera 2 kilometres across. Same region. Same underlying fire. Two very different ways of letting it out. The West Eifel whispers its volcanism in a scatter of pretty pools. The East Eifel, once, roared it, and the lake we are lying beside tonight is the scar of that roar, healed over now with water and reeds and the sound of monastery bells drifting across the surface in the evening. I want you to keep breathing slowly as we hold all of this together, because it is a lot of country to carry in the mind, and there is no need to carry it tightly. The Eifel, the Vulcan Eifel, named openly for its fire. The two fields, west and east, the Maars, those borrowed-named round waters. And in the middle of it, in the eastern field, 24 kilometres northwest of Koblenz, the caldera lake exhaling its old breath through the southeastern shallows. That is the shape of the ground. That is the family our lake belongs to. And the thing that makes our lake the one worth staying up for, or rather, worth falling asleep over, is that of all this scattered fire, all these round waters and fizzing springs and dark volcanic stones, Laacher See is the giant that hides best. It is the largest of them all, by an enormous margin, and it is the one almost no one outside these hills can name. Think, for a moment and gently, about how a thing that size manages to stay unknown. A volcano that erupted with the force this one did should, by rights, be a name every schoolchild recognizes. There are volcanoes on the far side of the planet, on islands and coastlines few of us will ever visit, whose eruptions we all learnt about, whose names arrive fully formed in the memory the moment someone says the word volcano. They earned that fame by erupting within human memory, within the reach of writing and photographs and newspapers and later of film, by killing, or by darkening skies over cities full of people who could record what they saw. They erupted where history was watching. And Laacher See, our lake, did its great work in a time before any of that. It erupted into a Europe of hunter-gatherers, into a world with no cities, no writing, no one to carve the date into stone or set it down on a page. It erupted, and then it went quiet, and then it filled with water and grew a fringe of reeds and became beautiful, and by the time anyone was keeping written records of the world, there was nothing here but a lovely lake and no memory at all of the night the sky turned to ash. The eruption was not hidden by the earth. It was hidden by time. It happened just far enough back that no one was left to remember it out loud. And so it sat, quietly, for thousands of years, the giant with no name, breathing its slow gas through the shallows, while people built an abbey on its shore, and quarried its stone, and fished in its waters, and never quite knowed what the round shape of the basin was trying to tell them. It took the patient work of geologists, reading the rock rather than any human record, to piece together what had happened here, to find the ash where it had fallen, to measure the caldera, to trace the gas back to its source, to understand that the calm was not the absence of a volcano, but the sleep of one. Everything we now know about this place, we know because the ground itself kept the record when no person could. The rock remembered what history forgot. That is where we are going, down into that record, into the layers the earth laid down on the night it emptied itself and the long, quiet centuries since. We will read the eruption itself before long, how a magma so full of gas built up beneath here, why it came out the way it did, how high the column climbed, and how far the ash was carried out across the whole face of the continent from one small lake in Germany. We will follow the strange story of what the eruption did to a great river, and the even stranger story of how, only a few years ago, the rings of long-dead trees allowed scientists to pin the exact year it happened, and, in doing so, to correct something the whole world had believed about it. We will meet the people who lived beneath the ash. And then, at the very bottom of the night, we will come back up through the living evidence, the bubbles, the deep faint tremors, the slow rising of the land, and I will give you the honest answer to the question everyone eventually asks about a place like this. The answer that is calmer and more interesting than fear. But not yet. None of that yet. For now there is only the surface, the still water 275 meters above the distant sea, the reeds along the margin barely moving, the southeastern shallows where the silver threads of gas rise and break and rise again, patient as anything, the slow exhalation of a giant that has been asleep for 13,000 years and has not, in all that time, quite stopped breathing. Watch the bubbles a while longer in your mind. Let them rise and fade, in no hurry, asking nothing of you. There is a whole mountain of a story sleeping under that water, and we will go down to it together, one soft layer at a time. There is no rush at all. The lake has waited 13,000 years to be understood. It can wait through one more slow and gentle night while you drift, here at the edge of the still water, toward sleep. Notice how the light would fall on it, if you were there. Late afternoon, the sun low over the western rim of the caldera, the far shore already in shadow, and the whole surface gone to a soft pewter grey, flat and luminous at once. The abbey on the southwestern edge, catching the last of the light on its old stone towers. A single bird, perhaps, crossing the water without a sound. And down in the southeastern corner, where the shadows are deeper and the shallows are calm, those small columns of gas still climbing, still breaking the mirror in little rings. The only motion in all that stillness that comes not from the wind, not from the birds, not from anything above, but from below, from the dark, from the sleeping fire. The lake breathing out one more time into the cooling evening air, exactly as it has done every hour of every day, for longer than there have been cities anywhere on earth. Stay with that image as we begin, very slowly now, to go down. Down past the pewter surface into the cold, clear water. Down through the 53 meters of dark to the mud of the lake bed, where the gas seeps up in 1,000 tiny threads through the sediment. Down past the floor of the lake into the shattered rock of the old caldera, layer on layer of pale pumice and grey ash, the wreckage of the night the mountain emptied itself. And down still further, past all of that, toward the place where the story truly begins, kilometres beneath the reeds and the bells and the sleeping town, where a body of molten rock once gathered itself in the dark, grew heavy with gas, and waited for its one moment to reach the sky. That is where we are headed, you and I, over the hours ahead, toward the fire, and then back up into the light, with the whole shape of it understood at last. But we go the slow way, we go the way the water itself moves through this landscape, unhurried, finding its own level, in no particular hurry to arrive. So loosen your hold on the day now. Let the details soften. Let the map blur gently at its edges, Koblenz somewhere off to the southeast, the Rhine winding through its valley, the borders of Belgium and Luxembourg away to the west, and here, at the centre of it all, the round dark lake in its scar, still and grey and quietly breathing. Let all of it settle into the background hum of a story being told to you in the dark, and let yourself begin, at whatever pace you like, to drift. There is a great deal still to tell. The eruption is still ahead of us, and the ash and the river and the trees that gave up the date and the people and the deep tremors, and the rising ground, and the plume of hot rock reaching down toward the center of the earth. All of it still ahead, all of it waiting, as patiently as the lake itself, for us to come to it in our own slow time. And so we will begin, in the next slow while, to walk back down into the night the sky turned to ash, into the phonolite gathering in the dark beneath these gentle hills, into the great charged chamber of molten rock that had been sitting and changing and growing more dangerous for a very long time before it ever moved. Kilometres below the place where the reeds now grow, and the gas now rises, and the still grey water holds the trees upside down in the fading evening light. Begin with the chamber. That is where the story of the eruption truly starts, not with the fire and the noise of it, not with the column of ash that rose into the cold sky above these hills, but in the stillness of a much deeper darkness, kilometres below the surface, where the rock itself has passed through something like a long and very slow transformation. Phonolite, that is the name of what gathered there. It is the word geologists give to a particular kind of magma, one that has been sitting in the earth for long enough that it has changed its composition over time, becoming less like raw molten rock and more like something distilled and concentrated, the way a broth becomes a sauce when left to cook down slowly on a low flame. Phonolite is silica poor compared to the granite family rocks, but it is extraordinarily rich in dissolved gases, water vapor, carbon dioxide, sulfur compounds, all locked inside the melt, under pressure, the way carbonation is locked inside a bottle of sparkling water when the cap is screwed on tight. And like that bottle, it is the pressure that matters. While the cap holds, there is nothing to see. The fizz is invisible, held inside, patient, but the moment the pressure falls, the moment the cap begins to turn, what was invisible becomes violent, and becomes so with a speed that is difficult for the mind to follow. Phonolite is also, by its nature, viscous. This is the other half of the mechanism, and it is worth slowing down here to understand it, because it is the reason Laacher See behaved the way it did, rather than the way a gentler, more fluid volcano might. A low-viscosity magma, think of the thin, fast-moving lava that flows from the flanks of Hawaiian volcanoes, allows its dissolved gases to escape gradually and relatively quietly. The way a glass of gently poured beer loses its carbonation slowly over an hour, the bubbles have room to rise, and the gas bleeds off at the surface without any great drama. But a high-viscosity magma is more like cold treacle, thick and slow and resistant to movement. When gas tries to escape from inside that treacle, it cannot simply drift upward and disperse. It builds, and it builds. The bubbles cannot move fast enough through the surrounding melt to escape, and so the pressure inside the chamber, already enormous from the weight of kilometres of rock above it, grows more intense still, until the container simply cannot hold. The phonolite beneath what would become Laacher See had been sitting in its chamber for a very long time. The exact duration is not easily known, but geologists understand that this kind of magma, in this kind of tectonic setting, forms slowly, the result of mantle rock partially melting deep below the surface, and then rising and pooling and differentiating over periods that make even the 13,000 years since the eruption look brief. It gathered, and it evolved, and it concentrated its gases, and it waited. And underneath the weight of the hills, in the total darkness several kilometres below, what was then a cold late glacial landscape covered in tundra and birch scrub, it reached a point at which waiting was no longer possible. Geologists estimate that the eruption expelled somewhere in the region of 6 cubic kilometres of magma in dense rock equivalent terms. That phrase, dense rock equivalent, is a way of measuring volcanic output honestly, by accounting for the fact that when magma explodes and expands and fragments into ash and pumice, it takes up far more space than the original melt did. 6 cubic kilometres of solid rock, reduced to loose material, produces perhaps 16 to 20 cubic kilometres of tephra, the collective word for all the fragments a volcano throws out, from the finest particles of ash so small they can travel the length of a continent on upper-level winds, down to fist-sized lumps of pumice and larger blocks thrown bodily from the vent. 16 to 20 cubic kilometres of material. It is a number that asks to be pictured rather than simply heard and passed by. 16 to 20 cubic kilometres of loose volcanic matter, distributed in days or weeks across an area that includes what is now France and Sweden and the Baltic coast. Mountains range of soft grey and ochre debris, carried by wind and gravity into every hollow and river bend in the surrounding land. And then there was the column. To produce that volume of material, the energy released at the vent had to be enough to drive a plume of ash and gas and fragmented rock high into the atmosphere, not just the lower troposphere where weather lives, but up through it, 20 kilometres, 25, perhaps 35. Geologists estimate the eruption column rose somewhere between 20 and 35 kilometres, punching through the tropopause and into the stratosphere. The stratosphere is the layer of the atmosphere above the weather, where there is no rain to wash particles back down, no convective mixing to bring things back to the surface quickly. What gets into the stratosphere can stay there for months, circling the planet on high-altitude winds, scattering sunlight, cooling the surface of the Earth below. Pinatubo, in 1991, did the same thing, and the world was measurably cooler for the following year. Krakatau, in 1883, produced sunsets of such unusual colour that they were painted by artists across Europe and documented by the Royal Society. These are the comparisons that give honest scale to what happened above this round lake 13,000 years ago, and they are honest comparisons because Laacher See was a V6, which is the same broad category as Pinatubo and Krakatau. Events powerful enough to leave signatures not just in local geology, but in the record of human experience across entire hemispheres. It is worth resting with that for a moment. The scale comparison is not rhetorical. It is simply true. The eruption did not happen all at once. That would be too simple, and volcanoes rarely oblige with simplicity. What geologists have pieced together from the deposits, from the layered stratigraphy of ash and pumice and surge deposits that can be read in road cuts and quarry faces across the Eifel today, is that the eruption unfolded in phases, over a period of perhaps days, perhaps a few weeks. 3 main units are recognizable: the lower, middle, and upper Laacher See Tephra. Each one represents a different phase in the eruption's character, as the magma chamber emptied and changed, and the nature of what was being expelled shifted. The lower unit tends to represent the early, most violent discharge, the first release of the most gas-charged material sitting at the top of the chamber. The middle and upper units record how the eruption evolved as deeper, differently composed material made its way to the surface, and as the structure of the chamber itself began to collapse. Reading these layers is something like reading the chapters of a very compressed geological book, each page laid down in hours or days, one on top of the next, each carrying a different fingerprint of the conditions that produced it. During the most intense phases, pyroclastic density currents moved through the valleys around the vent. These are perhaps the most viscerally fearful product of an explosive eruption. Fast-moving, ground-hugging clouds of hot gas and fragmented rock and ash. Too dense to rise into the air, too powerful to be deflected by ordinary obstacles. Capable of travelling at speeds that make survival in their path essentially impossible. They pour downhill like an invisible avalanche of hot, ash-laden air, filling valleys and riverbeds, stripping vegetation from slopes, depositing meters of material in the topographic lows. The valleys running outward from what is now Laacher See carry the geological evidence of these flows in their stratigraphy, layers of welded or loosely bonded pyroclastic material. The frozen footprint of something that moved very fast a very long time ago, recorded now in the quiet walls of road cuts and in the material beneath the soil of the surrounding farmland. It is possible to drive through the Eifel today and be within a few meters of that record without knowing it is there, which is itself a kind of summary of the whole story. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And then the ash went out across the world. Not all of it, of course. The coarser material, the large pumice clasts, the blocks, the heaviest fragments, fell close to the vent, piling up in thick accumulations in the immediate surroundings, building the landscape that still characterizes the Eifel today, the lumpy, pitted, pale-toned ground that tells a geologically literate eye exactly what it is looking at. But the finer fractions, the dust-fine volcanic glass, the tiny shards of silica and feldspar, and the altered minerals of the phonolite, ground to microscopic fragments by the explosive decompression and the turbulent journey up through the eruption column, those were carried differently. In the upper levels of the column, the material reached heights where stratospheric winds took over, and what left the vent above what is now Western Germany was transported eastward and northward and southward on wind patterns that no longer exist in the same configuration but whose ancient paths can be reconstructed by finding where the ash eventually landed. The Laacher See Tephra, known in the scientific literature by its abbreviation EST, is one of the most important stratigraphic marker layers in all of European geology. It has been identified precisely, chemically, unambiguously in cores pulled from lake sediments and bogs and marine muds across an area that stretches from northern Italy in the south to southern Sweden and the shores of the Baltic in the north. That is an enormous swath of the continent. To the west, the ash reached into what is now France. To the northeast, particles of Laacher See phonolite glass have been found in sediments as far as the Baltic region. Wherever these particles land, they arrive at the same moment, the same weeks of the same year, the same brief window of geological time, falling from the same column of air. They are, in the most literal sense, a timestamp. This is what Tephra chronology uses. It is a word worth saying slowly because it carries an entire discipline inside it, tephro from the Greek for ash, and chronology from the Greek for time. Tephra chronology is the science of using volcanic ash layers to date the sedimentary sequences they fall into. If you are studying a lake in Sweden whose sediments have accumulated over 20,000 years, and somewhere in those sediments you find a thin band of grey glass particles that match chemically and mineralogically to the Laacher See eruption, you now have a fixed point in time. You know that everything below that layer is older than 13,000 years, and everything above it is younger. You know this not approximately, not by inference from the slow accumulation rate of organic material, but precisely because the ash fell at a specific moment, from a specific eruption, and the chemistry of the glass is as distinctive as a fingerprint. Scientists working on late glacial and early Holocene sediment sequences across Europe use the Lelst as a reference horizon, a shared zero point from which relative ages can be measured in many directions at once. And it was that same use, the precision with which a volcanic layer pins time, that led, in 2021, to one of the more significant revisions in our understanding of this period of European prehistory. Because the ash layer had always been dated by various methods to roughly 12,900 years ago, a figure that had been in wide circulation for decades. But researchers working with subfossil tree rings, the rings preserved in ancient wood that was buried or killed by the eruption itself and has been preserved since in the waterlogged sediments of the region, were able to apply a technique called dendrochronology, the reading of annual growth rings in trees, to the problem. Each year of a tree's life leaves a ring in its wood, thicker in good years and thinner in poor ones, and the pattern of wide and narrow rings across a long sequence is as individual as a barcode. By matching the patterns in subfossil wood from the eruption's path to existing ring chronologies from elsewhere in Europe, the researchers were able to pin the Laacher See eruption not to a rough decade, but to a specific calendar bracket. The study, by Reinig and colleagues, published in Nature in 2021, placed the eruption at 13,006 years before present, with an uncertainty of plus or minus 9 years. 13,006 years, give or take less than a decade. That revision, roughly 100 to 200 years older than the classic figure, sounds small. But in the context of this particular period of European climate history, it was not small at all, because it settled a question that had been genuinely open and genuinely contested for years. The question was whether the Laacher See eruption had caused, or at least contributed to, the onset of the Younger Dryas. The Younger Dryas is the name given to a sudden and severe cold reversal that interrupted the general warming trend at the end of the last ice age, plunging Europe and much of the North Atlantic region back into near-glacial conditions for roughly 1,000 years, beginning around 12,900 years ago. It is one of the most dramatic events in the climate record of the late Quaternary, and for a long time it seemed suggestively coincidental that a V6 eruption capable of injecting stratospheric aerosols that could cool the planet appeared to sit right at its threshold. The proximity in the old chronology was tantalizing enough that serious researchers proposed the connection. But 13,006 years before present is not 12,900. It is meaningfully earlier. The tree ring redating places the eruption approximately 130 years before the onset of the Younger Dryas cold snap. The eruption did not trigger the Great Cold Reversal. The two events were real, and they were large, and they happened close together in geological time, but they were separate. The Laacher See eruption almost certainly caused a period of regional cooling from its stratospheric aerosols, in the same way Pinatubo cooled the Northern Hemisphere briefly after 1991. But the Younger Dryas was something else, a reorganization of ocean circulation, a shift in the Atlantic's conveyor of warm water, a mechanism much larger and more deeply rooted in the climate system than a single eruption, however enormous, could have produced. The tree rings said so, plainly, by putting the eruption back to where it belonged. 130 years removed from the event it had long been suspected of causing. It is a good kind of correction. Not a correction that diminishes the eruption. A V6 event needs no embellishment from false association with larger catastrophes, but one that sharpens the picture, that places the event more precisely in its sequence. That removes a confusion and leaves the actual facts of it clearer and more remarkable on their own terms. The eruption was large enough to alter the climate briefly. It was not large enough to hold back the warming that was already underway across the northern hemisphere, nor was it the trigger for a millennium of cold. It was itself enormous, singular, complete, and that is more than enough. There is a period in the sequence worth naming, because it helps to understand what the world looked like in the years immediately before the eruption changed it. The Alad interstadial is the warm interval that preceded the Younger Dryas, a period of relative mildness and vegetational recovery during which birch and pine forests were spreading northward and westward across Europe, and the tundra that had characterized the continent during the glacial maximum was retreating. The Alad was not warm in any sense that would feel comfortable today, but it was measurably gentler than what had come before and what would come after. It was a pause in the cold, a window of growing things and moving people and changing landscapes, and it is in that window, in that spreading green moment of relative ease, that the eruption happened. The sky above the Eifel opened during a time when life was beginning to recover from the Ice Age, which is one of the things that makes the human dimension of the story particularly worth sitting with. Because there were people here. Not many people. By any measure that would be legible to a modern mind, the continent was sparsely settled, the groups small and mobile, the populations dependent on game and seasonal movement in ways that left light and easily erased traces in the archaeological record. But they were here, the hunter-gatherers of what archaeologists call the Federmesser culture. The name comes from a distinctive style of small curved blade found at their sites. The German word meaning roughly penknife were present across a broad swath of northwest and central Europe in the millennia around the eruption. They were adapted to the cold, late glacial landscape in ways that are not fully legible to us now. Their lifeways reconstructed from flint tools and occasional animal bones and the rare survival of organic material. But they were real people, in real settlements, however temporary, across the landscape that the ash would cover. The researcher Felix Riede has argued that the disruption caused by the Laacher See eruption was significant, that the ashfall depopulated large areas of the continent, that the cultural disruption reached further than the obvious immediate impact zone around the Eifel, and that traces of the demographic catastrophe can be read in the archaeological record of groups as far away as southern Scandinavia. The Brom culture, a group known from sites in what is now Denmark and southern Sweden and named for a site at Brom on Zealand, shows signs of cultural disruption in the archaeological sequence that Riede has proposed may be linked, directly or indirectly, to the cascading effects of the eruption, disrupted migration routes, displaced population movements, changed resource distributions as the ecological landscape of large parts of Europe was altered under a layer of ash. This interpretation is credible and carefully argued, and it is also genuinely debated. Other archaeologists are not fully convinced of the chain of causation, and the evidence is imperfect and incomplete, as evidence from the deep Paleolithic so often is. But what is not debated is that the ash fell, Centimetres of it, in some areas more, blanketing the ground, suffocating vegetation, contaminating water sources, disrupting the movement of animals, covering the traces of the people who had been living there with a pale geological shroud. Whatever happened to the specific individuals who were present when the eruption began, and we cannot know, and will not know, the landscape they occupied was changed in ways that were not reversible on any human timescale. The soil would have taken decades to recover. The forests would have taken longer. The animals that depended on those forests and those plants would have moved or perished. The people would have had to move or perish too. It is not embellishment to call it a catastrophe. It is simply description. And now consider the silence around it. Pinatubo erupted in 1991 on the island of Luzon in the Philippines, in the middle of a world equipped with satellites and seismometers and international reporting and photograph and film and the full apparatus of modern record-keeping. The eruption is remembered and documented and studied, and its effects on global climate are still analysed and published decades later. Krakatau erupted in 1883, in the age of the telegraph, when the shockwave from the explosion circled the planet 4 times and was recorded by barographs in Europe, and the sound was heard in Australia. The sunsets it produced inspired painters and were reported in newspapers across the world. Both eruptions are part of the permanent record of human memory. Both are household names, or nearly so, to anyone who reads about natural history or science. Laacher See erupted at a scale comparable to both of them, and almost no one outside the community of volcanologists and geologists and archaeologists who study this period has ever heard of it. There is no written account because there was no writing, not anywhere in the world, for another 8,000 or 9,000 years after the eruption. There is no monument to it because the people who survived it left no monuments. There is no oral tradition, no myth recorded in any surviving form, no song, no painting, no institutional memory of any kind. The eruption happened in deep time, in the pre-linguistic past of a species that had not yet invented the means by which it records and transmits experience. And so it vanished, not from the geological record, where it is perfectly and permanently preserved, but from the human one. A V6 event, the scale of Krakatau and Pinatubo, became a secret that only the rock knew. And the rock kept it for 13,000 years, until the geologists came with their hammers and their chemical laboratories and their curiosity, and began, very carefully, to read it back. That is the hidden giant paradox, stated plainly. Not a mystery, not a conspiracy, not an oversight of scholarship, simply the consequence of time. Events that happen before the written word leave no human memory. They leave geology. And geology speaks to those who have learned its language, and not to those who haven't. And so the great eruption of Laacher See sits in its round lake in its gentle German valley, surrounded by weekend visitors and cyclists, and the bells of the Abbey on the southwestern shore, and most of the people who come to it and rest on its banks and watch the light change on its surface have no idea that the very bowl they are looking at is the scar of something that would have been the most significant natural event in human memory, if only there had been any memory to hold it. The pumice is still there, in the ground. The ash is still there, in the bogs and lake beds across the continent, a thin grey line pressed between the layers of organic sediment like a page in a book. The caldera is still there, filled with its quiet water. And the ground beneath it is still there, still warm, still moving, still sending its quiet signals upward through the kilometres of rock that separate the surface world from the hot and restless interior. But that is for the next slow descending chapter of this story, which will come in its own time. For now it is enough to be here with the ash layer, the Laacher See Tephra, the Lest. That single horizon of volcanic glass and phonolite particles pressed into the sediments of a continent, a frozen record of a sky that turned grey and stayed grey for weeks above lands that stretched from the Mediterranean to the Baltic. A continent dusted from a single source, a single chamber, a single enormous exhalation that has been sitting in the earth recording its own account of what happened long before anyone was here to listen. The ash is still in the bogs, it is still readable, it is still telling the time across hundreds of thousands of square kilometres of European sediment to anyone patient and knowledgeable enough to look. And somewhere along the southeastern shore of the lake, in the shallow water where the reeds thin out and the bottom is visible in the pale evenings, something else is still happening, something quieter, something slower, something that does not announce itself in columns of ash or columns of smoke, but in small, continuous, almost imperceptible streams of bubbles rising through the cold water from the sediment below. Those bubbles are not nothing. They are not the ordinary off-gassing of decomposing organic matter, not the slow bacterial work that produces methane in any rich-bottomed lake. Chemical analysis has confirmed it. The carbon dioxide rising through the southeastern shallows of Laacher See carries the isotopic signature of the mantle. It is magmatic gas. It is the breath of the same deep system that once filled a chamber kilometres below this ground with hot phonolite melt, pressurized it beyond what the overlying rock could hold, and then released it all at once into a sky that was, on the morning it happened, probably indistinguishable from any other late glacial morning over the Eifel hills. To understand why that release was so violent, it helps to understand what phonolite is and what it had been doing in the dark for a long time before the eruption. Phonolite is not a common magma, it is evolved, meaning it has sat and changed for a long geological while, slowly differentiating as the heavier minerals cooled and settled out, leaving behind a melt that was richer in silica, richer in sodium and potassium, and, crucially, richer in dissolved volcanic gases than the basaltic magma that originally rose from the mantle beneath the Eifel. Water, carbon dioxide, sulfur compounds, these were held in solution inside the melt at pressure, the way carbonation is held in a sealed bottle, kept liquid and quiet only by the weight of the kilometres of rock above. And the chamber that held all of this sat several kilometres down, beneath what is now the caldera, beneath the lake, beneath the abbey's quiet garden, beneath the reed beds and the moffettes and the cold water where the bubbles still rise. It sat there, filling and differentiating across an interval of time that dwarfs anything human memory can comfortably hold. When the pressure became too great, when the roof of the chamber could no longer carry the load, the gas came out of solution. All at once. The physics of that transition are simple and terrible dissolved gas exsolving from melt expands with enormous force, shredding the magma into fragments, accelerating the whole mass upward through the conduit. The eruption column that resulted rose somewhere between 20 and 35 kilometres into the atmosphere. It reached the stratosphere, it pushed above the weather, above the clouds, above the ordinary circulation of the lower air, and there the finest ash and the sulphur aerosols spread outward on the high-altitude winds in a thin, continent-wide veil. What came out of the ground was on the order of 6 cubic kilometres of magma, measured as dense rock, which expanded and fragmented into roughly 16 to 20 cubic kilometres of loose tephra, pumice, ash, and volcanic glass in every gradation, from boulder-sized blocks to particles fine enough to remain suspended in the stratosphere for months. The volcanic explosivity index places this at V6, that is the same scale as Pinatubo in 1991, which cooled the planet's average temperature by roughly half a degree Celsius for more than a year. It is the same scale as Krakatau in 1883, whose pressure wave circled the globe several times and whose sunsets reddened skies as far away as Norway and New York for 2 years. And it happened here, above this lake, above this valley in western Germany, in a landscape that today seems almost aggressively gentle. The eruption did not happen all at once in a single instantaneous detonation. Geologists read the deposits in 3 distinct units, the lower, middle and upper Laacher See Tephra, each representing a phase of the eruption as the character of the magma being drawn from different levels of the changed over days, or perhaps weeks. The lower deposits record the initial violent opening of the conduit. The middle and upper record the long, sustained, shifting continuation. While this sequence unfolded, pyroclastic density currents, low, fast, ground-hugging flows of hot gas and fragmented rock, moving faster than any living thing could run, poured down the valleys, radiating outward from the vent, burning and burying everything in their path. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And then the ash continued to fall. Not just here, not just in the Eifel and the Rhine Valley and the hills immediately surrounding the caldera, but across the continent. The Laacher See Tephra, the lust, has been identified in lake sediments and peat bogs from northern Italy and southern France to southern Sweden and the shores of the Baltic. A single eruption from a single chamber beneath what is now a quiet recreational lake left a chemically identifiable horizon across an area measured in hundreds of thousands of square kilometres of European sediment. Geologists and archaeologists now use that horizon as a precision clock, a tephrochronological timestamp so reliable that it can anchor the dating of other events in other sediments wherever the ash fell. A pollen record from a Swedish bog, a charcoal layer from a French river valley, an archaeological deposit from a site near the North Sea coast, all of them lined up, synchronized, referenced against a single afternoon of sky above the Eifel. The ash is the clock, and it is still keeping time. But the ash was only one part of what the eruption left behind on the land. There was something else, something that moved not through the air, but along the ground, following the lowest and most ancient route available to it, which was the valley of the Rhine. Think of the Rhine as the landscape's spine. It runs north and northwest from the Alps, gathering water from hundreds of tributaries, cutting through gorges and river plains that have been carved over millions of years, and the Eifel sits along the left bank of that river's middle reaches, where the valley is relatively narrow and the gorge walls rise steeply on both sides. When the eruption began, the material that came out of the vent did not simply fall on the surrounding hills and stay there. The pyroclastic density currents had already travelled down the radial valleys, and the eruption column was shedding ash across the continent, but the heavier tephra, The pumice and coarser fragments accumulated in enormous quantities in the valleys leading toward the Rhine. And the Brohl, the valley of the Brohlbach stream, connects almost directly from the caldera region toward the Rhine at the town of Brohl, where the Brohlbach meets the larger river on its left bank. That corridor became a conduit. The Tephra filled the Brohl. It filled it not in the gradual, gentle way that sediment accumulates over centuries, but suddenly, massively, in a single episode of geological violence that deposited material meters deep across the valley floor. And where the Brohl meets the Rhine, all of that material, the pumice, the ash, the rock, acted as a plug. It blocked the Rhine. Not metaphorically, not partially. The valley was dammed. Imagine the Rhine, which even then was a substantial river carrying the meltwater from retreating ice sheets across a landscape still slowly recovering from the last glacial maximum. Imagine that river suddenly finding its valley blocked by a wall of volcanic debris. The water backed up. A temporary lake formed upstream of the blockage, behind the natural dam created at Brohl. It may have taken days, or it may have taken longer, but the water behind that dam would have been building pressure with every hour, pressing against a barrier made not of bedrock, but of loose, unconsolidated tephra, the kind of material that once saturated with water does not hold. And then the dam failed. The outburst flood that followed carried pumice down the Rhine valley toward the north, and the evidence for it is still there in the sediment record. Laacher See pumice has been found redeposited far down the Rhine system, carried by the floodwaters hundreds of kilometres toward what is now the Netherlands and the North Sea coast. Think of fragments of pale, porous volcanic rock. The same rock that had been blasted from several kilometres below the ground by a column of gas and heat reaching 30 kilometres into the sky, riding a river flood through the gorges of the Middle Rhine and out across the lower plains, eventually settling into river gravels and floodplain sediments where geologists would find them, centuries and millennia later, and read in them the story of a day when the Rhine was not itself, but something stranger. It is a quiet kind of drama. The evidence for it does not announce itself. It sits in cross-sections of riverbank sediment, in the grain size and the sorting of ancient flood deposits, in the chemical signature of pumice fragments that have no business being this far from any volcanic source. No business, that is, unless you know about the dam and the outburst, and then everything makes sense. The Rhine was a carrier as well as a barrier. The eruption used the river the way a flood uses everything available, as transport, as reach, as a way of writing its message across the widest possible surface of the world. The tephra in the air, the pumice in the river, the ash in the bogs and lake beds, and peat columns across half a continent. And the question that all of this material eventually led scientists to ask, all of this precisely dated, chemically fingerprinted, carefully measured material, was the question of when, exactly, this happened. Not approximately. Not to the nearest 1,000 years, as precisely as the evidence could possibly allow. For a long time, the answer was roughly 12,900 years ago. That figure became the standard reference point in textbooks and review papers and popular accounts of the eruption. And it was a reasonable estimate, arrived at by various radiometric and stratigraphic methods, and consistent with what the ash layers revealed about their position relative to other datable events in the European Quaternary record. 12,900 years. A round, memorable number, the kind of figure that settles into the literature and tends to stay there Because once a date is in enough papers and textbooks and summaries, it becomes the thing everyone cites when they cite everyone else, and dislodging it requires not just a better estimate, but a better estimate published somewhere impossible to ignore. In 2021, that estimate was revised, and the revision came from an unexpected direction: subfossil trees. Trees that were alive at the time of the eruption and were killed by it, trees whose wood was preserved, waterlogged or buried in the sediments of the area affected by the ashfall. Wood preserves the rings it laid down year by year while it was alive, and those rings carry a record of growing conditions that can be read against the master chronologies that dendrochronologists, tree ring scientists, have built up over decades by overlapping ring sequences from living trees, historical timbers, and preserved ancient wood going back thousands of years. Friedrich Reinig and his colleagues, working with wood from trees that had been killed by the Laacher See eruption, were able to anchor those rings against the European tree ring chronologies and produce a new date for the eruption. Their study was published in Nature in 2021, and the date they arrived at was 13,006 years before present, with an uncertainty of plus or minus 9 years. 13,006 years. Not 12,900. The eruption was roughly 100 to 200 years older than the standard estimate. That may sound like a small adjustment. In human terms, in terms of the time between one generation and the next, or the span of a single person's working life, a century or two is considerable. But in geological time, where we routinely speak in millions of years, and even thousands of years tend to blur together, a revision of 100 or 200 years might seem trivial. The reason it is not trivial, the reason Reinig and colleagues published it in one of the most prestigious scientific journals in the world, and the reason it mattered so much, has to do with what else was happening around that time in European climate history. It has to do with a cold snap called the Younger Dryas. The Younger Dryas is one of the most dramatic climatic events of the late Quaternary. In the period after the last glacial maximum, as the great ice sheets were retreating and the climate of the northern hemisphere was slowly warming, a period of gradual recovery called the Alid interstadial, a relatively mild and biologically productive interval, something interrupted the warming. Abruptly, geologically almost instantaneously, the climate of the North Atlantic region swung back toward glacial conditions. Temperatures plummeted, the ice sheets stopped retreating and in some places re-advanced, forests retreated, the tundra expanded. And this cold reversal lasted roughly 1,000 years, from approximately 12,900 years ago to approximately 11,700 years ago. When the climate swung back toward warmth with equal abruptness, and the Holocene, the warm epoch in which we still live, began, the cause of the Younger Dryas is still debated. But one idea that gained considerable traction in the years before the Reinig study was that the Laacher See eruption had triggered it. The reasoning was superficially attractive. The eruption injected vast quantities of sulfur dioxide and other aerosols into the stratosphere. Stratospheric aerosols reflect sunlight. Reflected sunlight means less solar energy reaching the surface, less solar energy means cooling. And the timing seemed to fit. The 12,900-year date for the eruption and the 12,900-year onset of the Younger Dryas aligned suspiciously well. Perhaps, the idea went, the eruption tipped a climate system that was already near a threshold, pushing it across into the cold state. It was a satisfying story. Neat, causal, dramatic, a single eruption in western Germany causing a 1,000-year cold reversal across the northern hemisphere. That was the kind of geological narrative that captures attention and retains it, and it was repeated in enough popular accounts and secondary sources that it began to acquire the texture of established fact. The Reinig redating dismantled it. If the eruption occurred 13,006 years ago, it predates the onset of the Younger Dryas by approximately 130 years, and 130 years is not a rounding error. The aerosol cooling from a volcanic eruption, even a V6 eruption, even one that punched a column of sulfur into the stratosphere, dissipates over years, perhaps a few decades at most. The volcanic signal cannot stretch across a 130-year gap and then suddenly tip a climate system into a 1,000-year cold reversal. The physics do not allow it. The Laacher See eruption likely caused a brief regional cooling in the immediate years after it occurred. There is no reason to doubt that. A column of aerosol reaching 30 kilometres into the sky will scatter sunlight, and the scattered sunlight will cool the surface below it, and that cooling is real and measurable in the record, however faintly. But the Younger Dryas itself, that vast millennial cold snap, had its own cause or causes, separate from the eruption, and the redating proved the timing incompatible with any direct trigger relationship. So the eruption did not end an era of warmth. It did not plunge Europe back into something resembling the Ice Age. It erupted into the Alad interstadial, that mild interlude when the landscape of Central Europe was beginning to fill with birch and pine, and the first tentative advance of forest species northward, and the world after the eruption continued, climatically, more or less as it had been before it, for 130 years. Before the Younger Dryas arrived on its own terms and for its own reasons. This is a more honest story, and a stranger one in its way, because it removes the neat causal chain and replaces it with something harder to hold, two large events happening close together in time, but not, as it turns out, causally connected. The eruption was enormous. The Younger Dryas was enormous. They overlapped in human memory, or would have if there had been human memory to record them, but they were separate things. And there were humans. That is the part of this story that deserves to be held steady in the mind for a while, because it is easy to speak of geological time and volcanic events in terms so vast and abstract that the human scale disappears entirely. But 13,000 years ago, the Eifel region and the Rhine Valley and the wider landscape of Western and Central Europe were not empty. They were occupied, not densely, not in the way that we would understand settlement, no villages, no permanent structures, no agriculture, but occupied nonetheless, by people who had lived here through the worst of the last glacial maximum and were still here as the climate slowly warmed, and who knew this landscape as their home. These were late glacial hunter-gatherers. Associated with what archaeologists call the Federmesser culture, the name derived from a characteristic small blade shaped like a penknife, the German word Federmesser, meaning literally feather knife or quill knife. They were sophisticated people, mobile, highly adapted to the periglacial landscape they inhabited, skilled in the making of stone tools, and presumably in every other practical art required to live in a world where survival depended entirely on what you could carry and what the land could give. They moved with the seasons, following animals, exploiting the rich margins of rivers and lakes, building shelters from materials that have not survived, leaving behind mainly their stone tools and, occasionally, the residue of their hearths. They lived in the Eifel, along the Rhine, in the valleys, and on the uplands of what is now western Germany and the neighbouring regions of France and Belgium and the Netherlands. And on the day the eruption began, however the sky first signalled it, whether by tremors underfoot or a distant column of smoke, or simply the sudden total darkening of the sky as the ash cloud moved overhead, those people had no framework within which to understand what was happening to their world. The ashfall would have been catastrophic. Not everywhere equally, the wind direction and the eruption dynamics mean the ash was not uniformly distributed. But across large areas, an ash layer centimetres or even decimeters deep would have blanketed the ground, killed vegetation, contaminated water sources, and made the landscape essentially uninhabitable for anyone dependent on it for food. Animals would have fled or died. The rivers would have been choked with tephra. The fish, the waterfowl, the grazing animals, the entire ecological web that supported these communities would have collapsed suddenly and without warning across a vast area. The researcher Felix Riedi has argued that the Laacher See eruption caused significant depopulation of large parts of Central Europe, that communities that had lived in the most heavily affected zones were displaced, moved, disrupted in ways that can be read, however faintly, in the archaeological record. The lithic, the stone tool, assemblages from the period after the eruption in some areas show discontinuity. Where there had been one tradition of tool-making, there is now another, or there is nothing, a gap. A silence in the archaeological sequence, as though the people who had lived there simply were not there anymore. Whether they died or fled or were assimilated into communities elsewhere, the archaeological evidence does not say clearly. The record is thin and fragmentary, as it always is for this period, and Ried's interpretation, while well argued and supported by a reading of the evidence from multiple regions, remains a matter of active discussion among archaeologists. There are those who see the depopulation signal as real and substantial, and those who see it as a less clear-cut pattern than Riedi suggests, and the debate is not resolved. What can be said is this: an eruption of the scale of Laacher See, blanking enormous areas of territory under meters of hot ash and destroying the ecological base on which every human community in the region depended, would have had consequences for human populations. What form those consequences took, and how long they lasted, and how far their effects rippled outward, is a question the record can only partially answer. One thread of that question runs north. Riedi has also explored a possible connection between the disruptions caused by the Laacher See eruption and changes in the archaeological record of hunter-gatherer groups in northern Europe and southern Scandinavia, particularly in what is called the Bromy tradition, a late glacial culture found mainly in what is now Denmark and southern Sweden. Whether the refugee movements or cultural disruptions caused by the eruption in Central Europe can be linked to changes in the Bromy culture further north is a hypothesis that is credible in principle and debated in detail. The distances involved, the fragmentary nature of the archaeological record, and the difficulty of precise synchronization across regions all make this a challenging question to resolve with confidence. But it is a real question, asked by serious researchers, and the fact that it can be asked at all says something about the scale of what Laacher See put into motion across a continent. Think of it this way. A single eruption in the hills west of the Rhine, lasting perhaps a few weeks in total, deposited enough material across enough territory to displace entire human populations, to alter the trajectory of cultural development across Central Europe, and to send ripples of consequence reaching perhaps as far as the shores of Scandinavia. The geological record and the archaeological record interlock here, in a way that is both sobering and, in a certain light, awe-inspiring, because it reminds you that what the Earth does is not separate from what people do, that the history of human culture is always also a history of geological events, and that the line between natural history and human history is, at certain moments, no line at all, and yet almost nobody knows the name of this eruption. That is the paradox that sits at the center of the story, and it deserves to be examined carefully, because it is not quite as strange as it first appears. Consider what you would need for an eruption to become famous. To enter the cultural memory of the civilization that experienced it, and to stay there, and to be passed down through the generations in writing and in legend and in the historical consciousness that eventually produces popular accounts and documentary films and textbook entries. You need witnesses who can record what happened. You need a tradition of recording, writing, or at least the kind of oral history complex enough to survive for centuries. You need continuity of civilization from the moment of the event through to the moment when records start to accumulate in forms that persist to the present. And ideally, you need the eruption to have affected people who were already building the kinds of complex interconnected societies that leave abundant traces in the archaeological and historical record. Pompeii was buried in 79 C. The Roman Empire was one of the most literate and administratively sophisticated civilizations in human history. Pliny the Younger wrote 2 letters describing the eruption and the death of his uncle. Those letters have survived for nearly 2,000 years. The city itself, buried under meters of ash and pumice, was excavated from the 18th century onward and became one of the most visited and written about archaeological sites in the world. The eruption that buried Pompeii is known to every educated person in the Western tradition. Krakatau erupted in 1883. There were telegraph cables connecting Indonesia to the rest of the world. The pressure wave from the eruption registered on barometers as far away as England. The ash cloud coloured sunsets around the globe for months, and the coloured sunsets were recorded and painted by artists who had no idea what was causing them. A committee was established to collect accounts. A scientific report was published. Krakatau entered the global consciousness not just as a geological event, but as a cultural one. Pinatubo erupted in 1991. There were satellites overhead recording the eruption column. There were volcanologists on the ground who had predicted it with enough accuracy to enable a partial evacuation that saved thousands of lives. The eruption was filmed, measured, modelled, and broadcast around the world. Its effects on global temperature were tracked in the years that followed. Laacher See erupted 13,000 years ago. There were no letters, no telegraph cables, no satellites, no volcanologists, no cities, no written languages, no states, no institutions that could produce or preserve a record. The people who experienced the eruption were extraordinary in their own right, mobile, skilled, deeply knowledgeable about their world, but they left no written account because writing did not exist, and whatever oral traditions they carried about the event, if any survived at all, did not survive in a form that reached the historical period or the archaeological record in any recognizable shape. And the landscape where the eruption occurred is, today, and probably for most of the period since the volcanic activity quieted, a gentle, green, agricultural and recreational landscape. The Eifel is not a dramatic place in the way that the slopes of Vesuvius or the flanks of Krakatau are dramatic. It does not have the bare lava fields and fumarolic venting and obvious volcanic landforms that signal clearly to the casual visitor that they are standing on something dangerous. It has rolling hills, dark forests, quiet crater lakes called maars, the softened outlines of ancient volcanic cones that have been weathered and overgrown for millennia. It has vineyards along the Moselle, it has picturesque villages and health spas and mineral water springs. It has, on the southwestern shore of Laacher See itself, a 12th century Benedictine abbey whose bell tower is reflected every morning in the still surface of the lake. This is not the landscape of a famous catastrophe. It is the landscape of a Sunday afternoon, and it has been the landscape of a Sunday afternoon, perhaps not always so peacefully inhabited, but green and quiet and apparently safe. For so long now that the catastrophe it conceals has had no opportunity to announce itself. There is no ruin to visit, no buried city, no monument to the dead. The eruption happened too long ago, and the people it affected left too few traces, and the landscape healed too thoroughly over the millennia that followed. And so the gap between what Laacher See actually did and what it is known to have done is one of the starkest in the geological record of Europe. Ave 6 eruption. Volcanic explosivity index 6. That designation places it in a category with Pinatubo, which erupted in the Philippines in 1991 and injected enough aerosol into the stratosphere to lower global average temperatures by roughly half a degree Celsius for the following year, to produce vivid sunsets across the world, and to influence weather patterns in the monsoon regions of Asia and Africa. It places it in a category with Krakatau, whose eruption in 1883 generated a pressure wave that circled the globe multiple times, triggered tsunamis that killed more than 30,000 people in the coastal communities of Java and Sumatra, and produced an atmospheric optical effect, the brilliant red and orange sunsets, that was documented by painters and meteorologists and ordinary letter writers across the northern hemisphere for years afterward. Both Pinatubo and Krakatau are famous. Krakatau is famous enough that its name is used as a byword for a certain kind of volcanic violence, a word that means something to people who could not tell you where the Sunda Strait is, or why the eruption of 1883 was preceded by months of precursory activity that was itself impressive by any ordinary measure. The name carries weight, it has entered the language, Laacher See has not. And the eruption that produced it, which ejected on the order of 6 cubic kilometres of magma, roughly 16 to 20 cubic kilometres of loose tephra in total, which blanketed an area of hundreds of thousands of square kilometres with a chemically identifiable ash layer which dammed the Rhine, which drove a flood of pumice toward the sea, which displaced and perhaps effectively destroyed the communities of late glacial hunter-gatherers who had made their lives in the affected landscape. That eruption is known today mainly to geologists, to archaeologists of the late glacial period, to specialists in tephrochronology, and to people who have stumbled across the fact that the serene lake they are swimming in, or sailing on, or walking beside is technically a caldera, the hidden giant. That phrase captures something real. Not because the eruption was hidden in any deliberate sense, geology does not conceal itself from anyone, but because the conditions that would have preserved its fame in the cultural memory of the civilization that experienced it simply did not exist. The people who lived through it had no way to write it down. The people who came after them over the following millennia did not know what had happened. And by the time the first written records began to accumulate in this part of Europe, by the time the Romans arrived and began quarrying the porous volcanic rock of the Eifel, the material they called trass and valued as a hydraulic additive for their concrete. And making notes about the landscape they found, the eruption was already so far in the past as to be entirely beyond the reach of any living tradition. The Romans quarried the products of the Laacher See eruption without knowing, so far as we can tell, that those products were the products of an eruption. The trass they quarried, the pumice they handled, the peculiar, light, porous character of the rock that underlies the Eifel landscape, all of it the legacy of a volcanic event that occurred 9,000 years before the first Roman legions crossed the Rhine. They used the material, they did not know its story. And so there is a quiet irony in the layers here. The ash that fell across half of Europe is now a precision tool for dating other events, a clock used by scientists to synchronize records from Sweden to northern Italy, from bogs and lake beds and peat columns that accumulated their sediments over thousands of years and happen to carry, embedded somewhere in their stratigraphy, a thin horizon of chemically distinctive glass shards that can only have come from one place, one eruption, one brief interval of geological violence in the western German uplands. The clock is everywhere. The event it records is almost nowhere in the cultural memory of the civilization that now lives above it. This is, in its way, the defining quality of the deep past. It is not inaccessible, it has left more traces than we can ever fully read, but it is silent in the sense that matters to us, which is the sense of narrative, of story, of one person telling another what they witnessed. The hunter-gatherers of the Federmesser culture who fled the ashfall or died beneath it had stories. They must have had stories. Oral traditions, knowledge systems, accumulated understanding of the world around them, complex enough to support a life in a periglacial landscape across many generations. Whatever they said about the eruption, whatever account they gave their children, if they survived, of the day the sky went dark and the ground shook and the hot clouds came down the valleys, is gone. Not suppressed. Not hidden, simply gone, carried away by the same impermanence that carries everything away when there is no technology for writing it down. What remains is the ash, the pumice in the river gravels, the carbon dioxide still rising through the water of a quiet lake in the hills west of the Rhine, where a Benedictine abbey stands on the shore and the bell rings at intervals across the still surface, and where, if you know where to look, in the southeastern shallows, the lake floor is marked by points where ribbons of gas rise steadily through the water, released from whatever is still breathing far below. That is where the story goes next. Down into the water, down into the ground, down through the evidence that the thing that did all of this, the phonolite magma, the deep chamber, the rising plume of hot mantle rock, is not finished, is not, in the most technical and precise sense of the word, dead, that it persists, in the ways that a geological system persists, slowly, deeply, without announcement, exhaling into the cold water of a lake that most people have never heard of, in a country that does not think of itself as volcanic. Above a column of anomalous mantle heat that reaches down through the crust and into the deep earth at depths the mind can barely picture. The clock is still running, and the volcano is still breathing. Begin with the water. Not the surface of it, which is what you see first, that flat, pale mirror of sky, the reeds along the margin moving in whatever wind comes off the hills, the slow circles a fish makes when it rises and falls back. Begin beneath the surface, in the southeastern shallows, where the lake floor is visible in clear weather, and where, if you watch the bottom carefully, and long enough, you will notice something that does not belong to an ordinary lake. Points on the sediment where the lake floor shifts, where a thread of something lighter rises, and then another and another, not one stream but many, scattered across the shallower ground near the southeastern shore, a quiet constellation of disturbance rising steadily through cold, still water toward the light. These are not air bubbles. They are not the ordinary exhalations of organic matter decomposing on a lake bed, the methane that escapes from settling leaves and dead insects. They are something older and more deliberate than that. They are carbon dioxide. Magmatic carbon dioxide, gas that has migrated upward from whatever body of superheated, volatile-laden material still exists in the crust below, following fractures and permeable zones through the rock until it reaches the water above and escapes into it, and then through it, rising in those steady, silent threads toward the surface of the lake. The word for a place where this gas escapes through soil or rock or water is moffett. It comes from the Italian, ultimately from a word meaning bad air, the kind of air that kills, and indeed. In volcanic regions where moffets open at the surface and the gas settles into low places, the carbon dioxide can accumulate to dangerous concentrations, heavy as it is, and colourless and odourless, pooling in cellars and hollows, asphyxiating whatever is unlucky enough to spend too long inside the invisible layer. In the wider Eifel, this is not merely a theoretical risk. The region is dense with natural CO2 springs, places where the same deep earth gas rises through groundwater and bubbles out at the surface, and there are documented cases where the gas has collected in low structures and been found at concentrations far beyond what a person can safely breathe. The same deep volcanic exhale that gave the Eifel its famous mineral waters, the sparkling, naturally carbonated springs that have been bottled and drunk and sold for centuries, the famous mineral waters of this region, whose bubbles are not added by a machine, but arrive already dissolved, pressed in from below by geological pressure, is also the gas that drifts quietly into old cellars on still nights and turns the air inside them into something quietly lethal. But in the lake itself, the situation is different, and the difference matters. Laacher See overturns. Twice a year, as the seasons change and the temperature of the water shifts at different depths, the lake undergoes what limnologists, the scientists who study lakes as systems, call stratification and then turnover. The water layers mix, the bottom water rises, the surface water sinks. And in that mixing, the dissolved gases that have been accumulating in the cold, still lower water, are released. Vented, the lake breathes out on a seasonal schedule, reliably, repeatedly, so that the CO2 never has the opportunity to build up in the deep water to truly catastrophic concentrations. This matters because there are lakes in the world where the turnover does not happen, where the water stratifies so completely and so permanently that dissolved volcanic gas builds for decades in the lowest layer until the water is charged with it like a sealed bottle under pressure, and then something disturbs the stratification. An earthquake, perhaps, or a landslide into the water, and the whole column releases at once, in a sudden catastrophic outgassing that sends a white cloud of CO2 across the surrounding landscape faster than people can run from it. Lake Nyos in Cameroon did this in 1986. The gas cloud it released killed approximately 1,800 people in the villages around it within a night, quietly, while they slept or while they simply stopped where they stood. It is one of the more terrible things a lake can do. And it is a thing that Laacher See, because of its regular seasonal overturning, is not in a position to do. The comparison is worth making, and worth making plainly, not to alarm, but because alarm without the correction is incomplete, and because the calm, honest truth is more interesting than the incomplete, frightening version. The lake breathes steadily. It does not hold its breath until something terrible happens. The gas rises through the shallows in quiet ribbons, a slow, continuous exhalation from far below, and the water mixes and vents, and the cycle continues through the years and the decades and the centuries in which the abbey on the southwestern shore has stood there watching. What the bubbles in the southeastern shallows represent, set aside the question of danger, is something extraordinary. They are a direct physical connection between the world you can see and the world far below that you cannot see. Each one of those rising threads of carbon dioxide has come from depth. From whatever source, deep in the rock, still possesses the heat and the chemistry and the volatile content to produce magmatic gas and send it upward. You cannot see the source. You cannot reach it. But you can watch its breath arrive at the surface of a lake in the hills of western Germany, in the shallows near the southeastern shore, and know that something is still down there. Not dead. Not cold. Something that has been exhaling since before the abbey was built, since before the Romans came to cut the trass from the hillsides, since before the last of the late glacial hunters walked the ridge above the caldera and looked down at the water below them. A water that had not always been there, that had appeared in their recent memory, or in their parents' memory, or their grandparents' memory, filling slowly in the crater that the eruption left behind. A new lake in a new landscape, fed by groundwater and rain, while the gas rose through it then, as it rises now. The gas is the most visible thing, the most picturable. A person standing at the right place on the southeastern shore, in calm weather when the water is clear, can see it. But it is not the only evidence that the system below is still active, still moving, still doing the things that geological systems do when they are not yet finished. There are other signals, less visible, that require instruments to detect, and they are in their own way more significant. In the years between 2013 and 2018, seismometers in the region around Laacher See recorded something that seismologists classify as deep low-frequency earthquakes. The name requires unpacking because the word earthquake carries a particular image, something you feel. Something that rattles the windows and cracks the plaster and sends people into doorways. These were not that. They were events at depths of between roughly 10 and 40 kilometres beneath the surface, far deeper than most of the fault-slip earthquakes that shake the crust near its surface, and they were of a type, a signature, that seismologists associate not with rock breaking or faults grinding against one another, but with something else. With the movement of fluids, magmatic fluids, specifically material that is in some state between fully molten and fully solid, under pressure moving slowly through the rock. And the passage of that fluid creates a tremor with a characteristic low-frequency signature that trained instruments can distinguish from ordinary seismicity. The work that identified and characterized these events was published in 2019 by Hensch and colleagues in the journal Geophysical Journal International. It is careful, methodical work. It does not claim that Laacher See is about to erupt. It does not sound any alarm. What it says, in the language that scientists use when they are describing observations, is that the earthquake signatures recorded beneath the area during those 5 years are consistent with the movement of magmatic fluids at depth, and that this is evidence that the volcanic system in the region is not inert, not finished. still engaged in the kind of internal processes, pressurized fluid migration through fracture networks deep in the crust, that are expected of a system that has not shut down. Think of it this way. A fire that has gone out leaves cold ash, nothing more. But a fire that is banked for the night, covered, breathing slowly, not burning visibly, will still creak and shift in the grate as the materials inside it settle and move and slowly cool and slowly heat again. The sounds it makes are not the sounds of active burning, but they are not the sounds of extinction either. The deep low-frequency earthquakes beneath Laacher See between 2013 and 2018 were something like those sounds, the evidence of a system not burning but not cold. And then there is the ground itself. In 2020, a study published by Kremer and colleagues, also in the Geophysical Journal International, used GPS measurements. The same technology that navigates aircraft and tells a phone where it is on a map, but applied with much greater precision to the ground itself, using stations anchored in bedrock and measuring positions to millimetre accuracy over years to detect something across a broad region centred on the Eifel. The ground is rising, not dramatically, not in any way a person could notice in a lifetime of walking the hills, but measurably in the patient arithmetic of geodetic science. The land surface across parts of Western Germany and extending into Belgium and Luxembourg is moving upward and also spreading slightly outward from a centre point, uplift, on the order of about 1 millimetre per year. 1 millimetre per year does not sound like much. It is less than the thickness of a fingernail. But multiplied across decades, across the area of 3 countries, and understood in the context of what would produce such a movement, it is a significant signal. The pattern, uplift and lateral spreading from a point, is consistent with what you would expect if something buoyant and hot were pushing up from below. Something less dense than the rock around it, rising through the mantle as a warmer body rises through cooler fluid, pushing the overlying crust gently upward as it comes. A plume. The Eifel plume. The existence of a mantle plume beneath the Eifel had been imaged earlier by seismic tomography, a technique that works rather like a medical CT scan, but uses the waves generated by distant earthquakes rather than X-rays, and maps the interior of the Earth by measuring how fast those waves travel through different regions. Material that is hotter than its surroundings transmits seismic waves more slowly. Material that is colder or denser transmits them faster. By collecting many measurements from many earthquakes recorded by many seismometers and running the mathematics, scientists can build a 3-dimensional picture of the Earth's interior the way a radiologist builds a picture of a patient's internal anatomy. The work of Ritter and colleagues, published in 2001 and refined by subsequent imaging, identified in this way a column of anomalously slow mantle material beneath the Eifel, hotter than what surrounds it, less dense. Rising, the column reaches down to depths on the order of 400 kilometres. 400 kilometres. The cruising altitude of an airliner is roughly 10 kilometres above the ground. This column of hot mantle rock extends downward a distance 40 times greater than that, a deep root of thermal anomaly in the Earth's interior, the slow engine beneath everything that has ever happened in this landscape. This is the Eifel plume, and it is the reason for all of it. The reason for the East and West Eifel volcanic fields, for the Mars and the calderas, for the phonolite magma that differentiated in a chamber kilometres below the surface and then erupted 13,000 years ago with the force of Krakatau or Pinatubo. The reason for the CO2 rising through the lake bed in the southeastern shallows, The reason for the deep low-frequency tremors recorded between 2013 and 2018. And the reason, consistent with the geodetic evidence, that the ground across 3 countries is still slowly, quietly, by a millimetre each year being lifted from below. The plume is not a new thing, and it is not an emergency. It has been beneath the Eifel for a very long time, long enough to produce the long sequence of eruptions that built the volcanic fields, long enough for the Romans to quarry the rock it produced and add it to their hydraulic cement. But it is not a finished thing either. A 400-kilometre column of anomalously hot mantle rock is not an archaeological relic. It is an active geological feature, a live condition of the Earth's interior, and it will continue to do what it does: rise slowly, push the overlying crust, feed heat upward on timescales that have nothing to do with human schedules or human comfort. The Eifel volcanic region is classified as dormant, not extinct. The difference, in geological terms, is the difference between a person who is deeply asleep and a person who is gone. A dormant volcanic system is one that has not erupted in recorded time. In the case of the Eifel, the historical record of Europe goes back roughly 2,000 years, and there has been no eruption in that period, but which retains the structural and thermal conditions for future eruptions. An extinct volcanic system is one where the heat source has been cut off, where the rock above the former magma body has cooled and crystallized, and the whole architecture of an active volcano no longer exists. The Eifel is not that. The heat source, the plume, is still there, 400 kilometers down. The CO2 is still rising. The deep tremors happened in living memory. Within the last decade, the ground is still moving upward at a millimetre per year, and the Eifel has erupted more recently than Laacher See. The Ulmener Maar, in the West Eifel Volcanic Field, a small, round, steep-sided crater lake west of the East Eifel Fields, was formed approximately 11,000 years ago. 11,000 years, not 13,000. It is the youngest volcanic event in Germany. The youngest, by a measure of 2,000 years, of any volcanic event in Central Europe. And it is a maar, that peculiarly Eifel word for a crater blasted by a phreatomagmatic explosion, water meeting rising magma, and the encounter reducing everything above to flying fragments, which means the youngest eruption in this country was, when it happened, a violent thing. Not a slow, quiet lava flow, an explosion. The landscape absorbed it. Trees grew over the ejecta layer, the crater filled with water. Time passed. And the lake called the Ulmener Maar is today, like Laacher See, a calm and beautiful body of water reflecting the sky. There is no eruption forecast for the Eifel. There is no credible scientific evidence that an eruption is imminent, or that one will occur in any human meaningful time frame. The monitoring that exists in the region, the seismometers that recorded the deep low-frequency events, the GPS networks that measure the geodetic movements, the gas sampling that tracks the CO2 output from the lakebed and from the surface vents in the surrounding landscape, exists not because an eruption is expected, but because the system is demonstrably alive and because the consequences of a V6 eruption in the centre of 21st century Europe are serious enough to warrant watching. You monitor a sleeping system with a history like this, not because you are afraid of what it will do tonight, but because knowledge is always preferable to surprise, and because what you learn while watching a quiet system teaches you things about how it works that will matter if it ever begins to stir. This is not the same as saying it is dangerous, it is saying it is real. A real geological system with a real heat source in a real landscape where real people live, and where, for nearly 1,000 years, a Benedictine abbey has stood on the southwestern shore, and the monks have rung their bell across the water and tended their gardens in the volcanic soil, and received their guests and prayed their prayers above a caldera whose age and violence they could not have guessed, in an architecture built partly from the products of that violence. Maria Laach Abbey, Abtei Maria Laach, was begun in 1093 by the Count Palatine Henry II of Laach on the southwestern shore of the lake that gives it its name. Laach, the old name for the lake, is itself derived from the Latin lacus, a lake, which is also where the geological term caldera lake comes from, the naming of the water in this place by people who had no idea they were naming a caldera, who simply saw water and called it by the word for water, and built their church on its edge because it was a beautiful and sheltered place with stone nearby, and the means to grow things in rich volcanic ground. The Romanesque church at its heart is one of the more intact examples of that style in Germany, its thick walls and rounded arches and heavy towers, the signature of an architecture that was already ancient by the time the building was finished, and the community settled into its long life on the shore of the lake. The monks did not know, in 1093, what the lake was. They did not know it was a caldera. They did not know that the gentle hills around them were the eroded remnants of a cone that had destroyed itself in an explosion of stratospheric scale 13,000 years earlier. They did not know that the rounded shape of the lake was not an accident of the terrain, but the signature of a catastrophe so large that its ash had fallen across most of a continent. They knew only the water and the stone and the soil that grew things in the way that volcanic soils grow things, richly, prolifically, because the minerals in erupted and weathered rock are extraordinarily fertile, and the quiet that a place set into a natural bowl tends to have, shielded from the worst of the wind by the caldera walls rising around it. The stone they built with, the stone that the Romans before them had quarried and valued and shipped and used, is trass. The word itself is from this region, and the material it describes is the welded and consolidated volcanic deposits of the Eifel eruptions, a light, porous, glassy rock, pale yellow or grey, soft enough to cut easily but durable once in place. The Romans understood, from experience rather than chemistry, that when you ground this trass into powder and added it to lime mortar, the result was a cement that set hard even under water and resisted the salt and the damp in ways that ordinary lime mortar did not. They called a similar volcanic ash from the deposits near Pozzuoli in Italy Pozzolana, and the same principle applies to Eifel trass. The silica in the volcanic glass reacts with calcium hydroxide in the presence of water to form a cement-like compound that hardens and endures. Roman engineers building along the Rhine and through the provinces of Germania had access to Eifel trass from the Brohl valley, where the eruption deposits lay in deep accessible layers, and they used it. The aqueducts and baths and city walls of the Roman Rhineland were made, in part, from the products of the Laacher See eruption and the volcanic fields around it. From the same phonolite and tephra that had devastated the landscape 13,000 years before. Reduced by time and erosion and the work of human hands into a useful building material pressed into the service of empire. It is a strange continuity to sit with. The ash that fell from a stratospheric column and settled across half a continent. that buried the camps of hunter-gatherers and choked the Rhine and rode the outburst flood toward the sea, that same material, shifted and weathered and quarried, became the cement in aqueducts that carried water to Roman cities. And the caldera it came from became a lake. And on the shore of that lake, an abbey was built in 1093. And the abbey is still there, and the bell still rings. And if you go on a clear, calm day and stand at the right place near the southeastern shore of the lake, you can watch the CO2 rise through the shallow water in quiet, steady ribbons, the breath of whatever is still alive below. This is the thing that the surface of the lake conceals, and that the surface of the story conceals too, when the story is told quickly or carelessly. The surface of a calm lake tells you nothing about what is underneath it. A lake can be caldera deep, can sit in the ruin of a catastrophe, can be fed by rainfall and surrounded by reed beds, and visited by herons, and sailed by small boats on summer weekends, and still be connected, through fractures in the rock and columns of anomalous mantle heat, to a system that has not finished. The surface is honest. In a way, it really is calm. The lake really is peaceful. The herons really do fish there, but it is not complete. The calm is real. What it conceals is also real. And the concealment is, in the end, what this story is actually about. Not the violence of the past, which is documented and understood in as much detail as the ash layers and the tree rings and the riverine pumice can provide. Not the future, which is genuinely uncertain and which responsible science declines to predict in specific terms. But the fact of the gap, the fact that a lake above one of the largest eruptions in European history over the last 100,000 years, above a live mantle plume, above a region where deep low-frequency earthquakes signal magmatic fluid movement and geodetic measurements confirm that the ground is still rising, that this lake is essentially unknown, that most of the people alive today in Europe, the continent whose geological record it marks so precisely, have never heard its name, that you can drive through the green hills of the Eifel on a summer afternoon, past the Mars and the reed beds and the mineral water springs, past the Roman ruins built from volcanic stone, past the abbey on the crater rim, and never know that you are crossing a landscape formed by an event comparable to Krakatau in 1883, to Pinatubo in 1991, to every major volcanic eruption of the historical period that shook cities and darkened skies and cooled the planet for months. The reason it is hidden is simple and not conspiratorial. It happened 13,000 years ago, at a time when no one in this part of the world had writing, when there was no record-keeping beyond what could be carried in memory and passed from person to person in whatever language the Federmesser people used. By the time there was writing in this part of the world, by the time the Romans came with their Latin and their administrative habits and their quarrying operations, the eruption was as remote from them in time as the Roman Empire is remote from us now. More remote, actually, twice as remote. The landscape had healed itself so thoroughly that the most educated natural philosophers of the ancient world walked across it and saw hills, and a lake, and good volcanic soil, and did not guess at the scale of what had produced those things. The abbey was built above a catastrophe that nobody in 1093 knew had happened. The monks planted their garden in the rich volcanic earth and did not know why it was rich. The mineral springs were drunk and bottled and enjoyed without anyone understanding that the carbonation was magmatic in origin. And the modern world, inheriting this landscape and this lake, found it already absorbed into the ordinary, a hiking destination, a place to rent a boat, A pretty backdrop for the Romanesque towers of the abbey, and saw no reason to look further. But the instruments do not accept the ordinary at face value. The seismometers record what they record. The GPS stations measure what the ground is doing, 1 millimetre at a time, year after year. The geochemists trace the isotopic signature of the carbon dioxide rising through the lake and identify it as magmatic in origin, from below, from the system. The seismic tomography builds its picture of a 400-kilometre deep column of anomalous heat rising toward the surface from the mantle. And the result of all that careful, patient, instrument-mediated looking is a picture of a system that has no intention, has no awareness, has no schedule, but that is not finished. That is doing what it does, on its own timescale, in its own way, beneath the water and the reeds and the bell and the stone. What you take from a place like this, or from a story like this one, probably depends on what you brought to it. A person who came looking for danger will have found, perhaps, both more and less than they expected, more evidence that the system is alive and active, less certainty that this means anything threatening in any human time frame. A person who came looking for the scale of geological time will find it here, expressed in every layer, the hunter-gatherers who preceded the ash, the Romans who quarried the ash, the medieval monks who built on the ash, the 21st century scientists who measure the faint signals of the system that produced the ash, all of them arranged in sequence over 13,000 years and more. Each layer as thin as a bedding plane in the deposits of the Laacher See Tephra compared to the depth of time below them. And a person who came simply because they wanted somewhere quiet to rest their mind tonight will find, I hope, the thing they actually came for, which is this, that the world is old, that what looks still and ordinary is often the surface of something vast, that a calm lake in the hills of Germany, reflecting a grey morning sky, can sit above a system that has been breathing for longer than human memory reaches, and will continue to breathe when memory ends. And that this is not frightening, but simply true. The ordinary condition of a planet that is alive in its own way, on its own scale, according to its own unhurried rhythms. The water in the southeastern shallows is rising in those quiet threads right now, as it was rising yesterday, as it was rising when the Abbey bell rang this morning, as it was rising on the day in 2001 when the researchers published the first images of the plume 400 kilometres below. It will be rising tomorrow. The gas has been making this journey from whatever source of heat and chemistry persists in the rock below, up through the fractures, up through the cold water of the caldera lake, for longer than the Abbey has existed, for longer than any human structure in the landscape has existed. It will outlast what we have built here. The plume will go on rising. The ground will go on lifting 1 millimetre at a time. The lake will go on overturning twice a year, breathing out its accumulated gas and settling again into stillness. The heron will stand at the margin in the morning, and the boats will be pulled up on the shore in autumn, and the bell will ring at the canonical hours across the still water, and the Abbey will receive its guests. And somewhere far below all of that, below the roots of the Abbey's foundation stones, below the Roman quarry cuts in the hillside, below the compressed layers of tephra that mark the moment when all of this was very different, below the crust itself and down into the mantle at a depth that no instrument has ever physically reached, and no person will ever physically reach. The plume will go on doing what it does, hot, slow, patient, indifferent, alive in the only sense that geological systems are alive, which is to say, not finished yet. The lake has no memory. But the rock does. If you are somewhere comfortable right now, let that be enough. Let the image of the water settle, the shallows, the ribbons of gas, the still surface above them, the hills ringing the caldera in the dark, the lights of the abbey on the far shore where they have been visible for nearly 1,000 years. Let all of that go quiet. There are things in the world so old and so large that the only reasonable response is to stop trying to hold them and simply rest inside the fact of them. The way the water rests inside the caldera, contained and still above an ancient and continuing fire. If you feel moved to share where in the world you are listening from tonight, I would like to know. The comments are there, and I read them. There are more slow stories here, of the same careful and unhurried kind, whenever you want them. You have done enough for one evening. Whatever was not finished today will still be there. The lake will still be there. The plume beneath it will still be rising. None of it requires your attention tonight. Tie off here at the Wisdom Docks. The tide will wait till morning.